Welcome to build a scalable search engine using the Amazon Elasticsearch service. My name is Kevin Fallis. I am an AWS Principal Analytics Specialist Solutions Architect. Today's agenda, we're going to discuss the Amazon Elasticsearch service and its capabilities at a high level. We're then going to review search use cases that can be applied and leverage the Amazon Elasticsearch service. We're also going to deep dive on best practices for scaling search clusters. And finally, we're going to wrap things up with a demo. The demo is a simple search application that is a React-based framework that leverages API Gateway and will interact with the Amazon Elasticsearch service to provide a movies listing database. This will be coupled with facets and other navigation tools that allow you to find relevant movies for your viewing needs. So let's go ahead and take a look at what the Amazon Elasticsearch service offers. First of all, the Amazon Elasticsearch service is a fully managed service. And it really makes it easy to deploy, manage, and run Elasticsearch coupled with Kibana effectively at scale, with industry-leading reliability, scalability, and security. Some of the capabilities and benefits that you'll get, again, it's a fully managed service. It provisions all the resources for your Elasticsearch cluster. It does this in a secure and compliant environment, and it gives you the ability to launch in any region of your choice within minutes to address your compliance needs. It offers Kibana as part of the service, and it gives direct access to the Elasticsearch APIs. And this makes it easy for your existing code and applications to work seamlessly with the service. It's cost-effective, offers pay-as-you-go pricing with on-demand, and it gives you features that are free of any licensing costs. And these are plugins that you can find in Kibana or tools and features like UltraWarm that give you cost-saving options for long-term retention of valuable data. You can scale your cluster horizontally or vertically, and you can do this up to 3 petabytes of data per Amazon Elasticsearch domain. And you can do this with zero downtime through a single API call or a few clicks of the AWS Management Console. Additionally, you can leverage AWS CloudFormation and the AWS CLI to perform your scaling operations. Finally, the service is HIPAA eligible. It has the offerings of PCI DSS compliance, SOC 1, 2, and 3, FedRAMP Medium in AWS regions that are not GovCloud, and in AWS GovCloud regions in US East and US West, we offer FedRAMP High. Additionally, there are many ISO compliances too that the service provides to you already out of the box. One of the latest features that the Amazon Elasticsearch service offers is machine learning. Now, machine learning comes in many forms. First of all, we have a feature called anomaly detection, which is one of those plugins that I talked about that are free of any licensing fees. This allows you to scour across your data and do anomaly detection for certain patterns. Now, typically, anomaly detection is applied to log analytics, and today's topic is about search, but I wanted to call out that the machine learning offering that the service is providing to you also has a couple of other features that are very relevant to your search use cases. And one of those plugins is called K-nearest neighbors. Now, K-nearest neighbors gives you the ability to leverage vectors to go ahead and compare things such as images or other text and find similarity or matching or similar matching documents that could be leveraged in the return of a result set for your search needs. Also, you can leverage learn-to-rank models, which as you understand your query patterns, you can apply these learn-to-rank models to bring back more relevant information to your customers and your users of the Amazon Elasticsearch service in your applications. It's performant at scale, and the machine learning models are distributed and processed across the Elasticsearch nodes. So you don't have to stand up specific dedicated nodes to do these machine learning activities. Finally, it's easy to use. You don't have to have that machine learning expertise, and it's not required for you to do any machine learning background to leverage this service. You simply leverage the APIs, follow the instructions, and the service takes care of the machine learning, the k-nearest neighbors, and the learn to rank model activities for you. One of the primary things you look at when you're building at scale is the ability to access the data and control who can see what data. When you look at large quantities of data that may be in your index, you want to be able to protect that data. And as applications evolve, there might be different compliance or needs that you need to secure certain pieces of information, such as social security numbers or addresses or other PII data. You can leverage the security features on AWS to give you a secure solution for which you can house your PII data and protect it with many levers that gives you complete control of the data that gets returned back to your applications. So with the Amazon Elasticsearch service, we think of things as multi-layer security. And starting from the basic requests, with the service, you can enable HTTPS only, which will enforce secure HTTP for you to emit your data from your applications to the Amazon Elasticsearch service. Once a request arrives to the Amazon Elasticsearch service, you would leverage IAM to go ahead and validate whether or not the request, if it came from an automated process, is able to talk to the service and actually complete that action. If you're not programmatically accessing the service and you want to use Kibana to view some of the information in your search solutions, you can couple with Cognito to sign into Kibana. And you will also be able to use the Open Distro security features, which will give you the ability to provide roles on the cluster that can help you limit who gets access to what data. Once you're in the cluster itself, you're protected with the Amazon VPC. Now, VPC is considered what we'd call a virtual private cloud. It's all private networking, and the details of the Amazon Elasticsearch service endpoints will be presented in the VPC so that your applications can access the Amazon Elasticsearch service in a secure mechanism. Again, the Open Distro security features will give you control of what actions can be performed against a cluster, such as being able to read an index or not read from an index, or give you the ability to deny someone from changing the data that is in a specific index. When we look at the cluster itself, and we look at how data is communicated between the data nodes, we offer TLS version 1.2, which will securely allow the transmission of data between the data nodes for the Amazon Elasticsearch service. Finally, for your encryption at rest needs, you have the AWS Key Management Service. This allows you to bring your own keys to the Amazon Elasticsearch service, from which you control the master key and you own that encryption mechanism so that you can ensure that your data will be safe. So let's take a look at some of the availability, resiliency, and scalability features that the service offers. First of all, as I mentioned earlier, you can provision an Amazon Elasticsearch cluster in minutes. Through the API, the CLI, CloudFormation, or the console, you can change cluster properties such as the CPU specs, memory, storage, the instance types on AWS. You can choose compute-aligned instances, storage-aligned instances, or memory-aligned instances. You can scale these vertically or horizontally depending on the needs of your search solution. Again, you can leverage tools such as the APIs, AWS CLI, AWS CloudFormation, and the AWS console to perform these activities. Many customers will automate, so the APIs and CloudFormation are very popular options. Additionally, in the open source community, There are many other CI/CD pipeline tools that give you that capability and flexibility to build these scale events into your automation. Things such as Terraform come to mind when we think about some of the automation capabilities. Now, when it comes to scalability and availability, you can leverage multiple availability zones. And unlike any other cloud provider, AWS provides what are called AWS regions. Within AWS regions, we have availability zones, and availability zones are comprised of one-to-many data centers. And what this allows you to do is to build highly robust applications that can survive failure. Should an availability zone have an issue, you have other availability zones in which your Amazon Elasticsearch cluster can survive that event and still continue to function and serve up your search solutions. So using more than one availability zone can distribute your load and limit blast radius should there be an event in one specific availability zone. AZs, or availability zones as they're called, provide better availability as you scale your clusters for your search solutions. When you use 2 or 3 availability zones with dedicated master nodes, you're covered by the service SLA. Now, probably about a year ago, maybe a little bit more than a year ago, we increased our availability capability with 3 AZ deployments. Prior to that, it used to be 2 availability zones. Now, 3 AZ deployments will further limit the risks, and they provide for better availability as you size and scale your clusters to address your needs as you grow your search solutions. So let's say by rare chance that an AZ is unavailable. In this case, if that AZ was not there, you would lose only 1/3 of your compute and JVM capacity when it comes to serving your search offering. Now, if you go ahead and leverage the proper number of replicas, the Amazon Elasticsearch service is constructed in such a way that it will deploy the primaries and replicas across those availability zones so that you can have 100% coverage of your data redundancy in the event of the AZ failure. So one of the recent introductions that help you with your scaling activities is cross-cluster search for the Amazon Elasticsearch service. This gives you increased scalability, efficiency, and availability by separating distinct workloads, and it works like so. Let's say that you have an Amazon Elasticsearch domain and you have a lot of search applications that are residing in the domain, effectively multi-tenant search applications. And should you have issues with that one Amazon Elasticsearch domain, you're going to affect all of those applications. Conversely, some applications could be chattier than others, and they might take the resources that you need for other search solutions on that same Amazon Elasticsearch domain. So you can actually split these domains up into multiple clusters. You can use cross-cluster search to then isolate those particular Amazon Elasticsearch domains, and you can tune those for the performance needs of those specific workloads. The Amazon Elasticsearch service supports many popular search use cases. In this next series of slides, I'm going to walk through what those use cases are. To start off with, I want to talk about a company called Compass. Compass uses Amazon Elasticsearch service to scale their search infrastructure and build a complete, scalable real estate home search solution. By using the industry-leading search and analytical tools provided by the Amazon Elasticsearch service, they make every listing in the company's catalog discoverable to customers, and it helps real estate professionals find and market and sell homes faster. Now, Compass leverages a broad range of tools, one of those being the Percolate API. And what they offer is a feature called Save Searches. So as you go and you browse the listings on the Compass website, you can specify multiple dimensions. These are typically represented as facets when you are searching across properties, such as show me all properties between 1 and 5 acres. Show me properties that are in, say, a place called Charleston, South Carolina, or Miami Beach, Florida. And you might want to qualify other dimensions, such as I need 3 bedrooms, or I want 2 bathrooms, or I want to have a 6-car garage. So with Compass and their real estate tools that they provide as their services, that give you that capability backed by the Amazon Elasticsearch service to give you a fast search experience. So when you need a fast search experience for your websites, data lake catalogs, or allow your users to find quick and relevant data, you can use the Amazon Elasticsearch service because it does deliver high quality and personalized search results for customers. So one of the many use cases that I see when I'm working with customers is in e-commerce and the media space. Now, when you look at e-commerce and media activities, and my demo will cover a media solution, you're basically wanting to find something that you either want to buy, or a movie that you want to watch, or music that you want to listen to. And they typically follow a similar pattern. What you have is a search bar, and this gives you auto completion and full text search. So there are suggestion APIs with Elasticsearch, and more specifically the Amazon Elasticsearch service, that can help you build navigation into a search bar that present a series of suggestions or strings that can help you find details that you're looking for. You also can find a user's ideal ordering of search results. So it's not enough for you just to provide search results through auto-completion. You really need to understand what a user is looking for. So Learn to Rank, which was recently introduced to the service in the form of a plugin that is free of any licensing costs, allows you to help build a user's ideal ordering of those search results using Learn to Rank models. When it comes to similarity matching, you can leverage, as I mentioned earlier in the discussion, K-nearest neighbors. Now again, K-nearest neighbors is built using vectors. And let's say that you have your cell phone and you take a picture of something that you'd like to buy. Let's say it's a brand new lawn tractor, or maybe it's a household appliance, and you don't really quite know what it is, but you saw it and you liked it. And so what you can do is you can leverage KNN in your applications. You can take that image from the cell phone, you could upload it as a search parameter, and the similarity matching with KNN can browse similar images in your inventory and provide back similar results that might match the picture that your customer took. So you can do this with music, text, and other media that you can get into a vector format. Finally, when you navigate on your websites, typically you're presented with a multitude of features. You may, if you're looking at music or media, you may have specific genres that you're interested in. You might like hard rock, you might like metal, you might like rap, country, even classical music, or other forms of ambient music if you so desire. And all of these, different categories can be displayed on your web pages, and we call this faceting. The banking industry is another popular search use case. So many of you will go to your banking website and you want to find an ATM, or you want to find, a kiosk or a place that you can conduct your banking business. And what this does is it leverages geospatial queries. So the Amazon Elasticsearch service and Elasticsearch in general has a geospatial data type that you can provide lat and long coordinates. And with these lat and long coordinates, you can do things such as a radius from a point. And typically this point's going to be your location, and you might say in your search results or in your search request, I want to find any banks or ATMs near me within 5 miles. And so using geospatial queries and the Amazon Elasticsearch service, you can define a radius. You can even define a polygon if you want to say within a specific county or a specific city. And what will happen is that Elasticsearch will scour across your data in your indexes and it will find those properties that match your request to find a bank near me. And then what you can do is you can use relevance to order those by distance. And then you can give the user that's looking for your bank the closest location to them to achieve their banking business. Additionally, if you go on your banking website, you will find that you can search historically transactions back for n number of years. Well, this is actually provided by search. And what banks will do is offer you the ability to find transactions by, say, dollar amount. This can be exact or it can be in between. Say that you wrote a check, say 20 days ago, and you wrote it for $400, but you don't quite know who you wrote it to, and you haven't seen that check cash. So what you can do is you can type in a query. You can provide dimensions. You might say that the payee just happened to be, someone that you bought something from, and you knew what the specific dates are. So you can enter these dimensions in, and you can query on these multiple dimensions to find those banking transactions that are relevant for your needs. So let's talk about some of the best practices for indexing. First of all, we have what's called slowly changing data, and I call this the cutover pattern with an alias. Now, when you talk about indexing data, especially with search use cases, you're really wanting to focus on the performance of the search, and you're wanting to limit the effects of multiple changes on indexes. For those of you that aren't aware of what happens when you change a document in Elasticsearch, it actually replaces the existing document with a new version, and it marks the old document as deleted. And so what this does is it means that over time, as you change documents, you have a large volume of deleted documents that are interleaved with the blocks that are being fetched from disk and memory, and it makes your searches a little bit slower over time. So some of the patterns that people will use with slowly changing data is that as they update the data, what they're going to do is initially populate an index. And in our use case, we're going to talk about a movies database, so I'm going to use movies as an example. But you can take your documents, you'll index it into an index called movies version 1. So you populate that index. Next, you create an alias called movies so that your client applications can actually hook into that and have no need to understand the underlying implementation of what index is actually housing the data. So as you're searching and your data starts to change, let's say you update every 24 hours and you completely replace that data set. Well, the next thing you do is you'll create a new version of the index on the same cluster. You'll want to make sure that you have enough storage. Typically, I suggest to customers use double the space and some wiggle room, and then build that new index up while the other index is serving. Now you can do these maintenance activities or the new indexing operation on off-peak periods. Typically search activities are cyclical in many cases. In some cases it might not be so, and I have other patterns for that. But what this allows you to do is that as you build up that new version, you can validate that new version of the index without affecting what's going on with the existing version. And once you're happy with the state of that data, you can go ahead and swap the alias. Now, swapping the alias basically is an alias update. There is a API, an alias API on Elasticsearch that gives you ability to change the alias to point from one index to another index or point to multiple indexes. And we'll talk a little bit more about this here in some of the later patterns. But what will happen now is that your latest version of the data will serve, and your old index is a fallback should there be any drastic issues. Once you're done, you can go ahead and drop that old index. And then you just go ahead and repeat this pattern as needed through your cyclical daily ingest activities or whatever your time frames could be for replacing that current index with a newer, fresher version of the data. The next pattern deals with quickly changing data with a large footprint. And we're talking, in some cases, the magnitude of, terabytes, hundreds of terabytes or more. And it's not sustainable to build a large index to house all that data, especially if you are changing that data a lot and that data is growing rapidly. Now, this wouldn't be a login use case. Again, it's going to be a search use case. But the idea here is that you break the corpus of that data into multiple indexes. And you take a page from databases, which is using what would be called a partitioning strategy. Now, Elasticsearch itself does partition your data into multiple shards, but this is taking it up to a higher level. And we're talking about index level and treating indexes as separate partitions. And the idea here is that you break that corpus into multiple indexes and use a hash or some partitioning scheme. It could be date, but in most cases, you're going to select an ID that's not the doc ID. And in this case, I might use a movie ID. And I might do a mod 10. Now I'm only showing 4 indexes here, but I could usually use that mod 10 to roll out to 10 total indexes. But for the sake of discussion here, I have 4 different indexes. I perform a mod 10, and let's say I have movie ID 36644. If I do a modulo on that, the number 4 will come out, and I can use that to append to the name of my index to then write that data to that specific index. I don't affect any of the other indexes. I can do this at scale. And what this allows me to do is to organize docs with the same mod value into the same index. Now, all of us know that highly cardinal values get a nice even distribution in distributed databases and distributed solutions. But when you start partitioning data, sometimes you'll have different fill rates. And what this means is that those indexes you can individually tune based on the fill rate or the workload on those in aggregate. So in the end, mod 1 is going to have all IDs that end with 1. Mod 2 is going to have all IDs that end with 2. Mod 3 is going to have all IDs that end with 3, and mod 4 is going to have all IDs that end with 4, and so forth until the pattern's complete. Now we have data that's broken down. How do we search it? In the end, we can put, again, an alias on top of that. We can call it movies, and we can add all these movies indexes that are partitioned into the alias so I can search the entire corpus. Now, when I need to do maintenance activities, I only have to focus on one index. So let's say that movies partition 1 needs to do a force merge so I can clean up deleted documents. I can mark that as read only. I can do my force merge activities. I can still read from it. I can pause ingest to that specific index. I don't affect the activity to the other indexes that comprise that whole alias or that corpus of my document. And so this allows me to break those maintenance chores up and focus on what's really necessary. So in this case, I might have to reindex movies partition V2. So all I do is I then reindex from the existing index to the new index with the new index pattern that I want, whether it be adjusting my shards or other key dimensions on it. And I go ahead and I swap that index into my existing alias. And I'm now pointing at movies partition V4 version 2, and I can go ahead and drop the old movies partition. And this makes a really easy way for me to manage at scale my data ingest and my query activities. Another best practice to use is pre-indexing. With the Amazon Elasticsearch service and Elasticsearch in general, you can use bucketing and aggregations to do your work, but sometimes you really don't have to do a lot of that work. So for example, do you really need a long string field that can be expressed as enumeration? In one of my labs that I offer to customers, I do VPC flow logs. VPC flow logs have fields called no data or allow or deny, and these can be expressed as integers. So it's much more efficient from a storage perspective to express things as integers, and then your application can then wrap and do the mapping from an integer to a nice pretty string field in your application. And integers actually store as less space on disk, and they're a little bit more performant when it comes to searching. You can also look at ranges. So you can say, if in my real estate example, I want to find properties between 100,000 and 150,000, or I might want to find other properties from $300,000 to $1 million. You can express that range as an enumeration, and you don't have to do bucketing and aggregations to get that. You do a simple filter with Elasticsearch, and it's much more performant. And so using a pre-indexing model, you can prepare your data in such a way that it makes it more performant. So finally, we're going to wrap up the best practices with sharding. Sharding is one of the many things that many customers have challenges with, and they want to understand how do I make this more efficient. So I do have some simple patterns that we can leverage here. The first one is if I have a number of data nodes and I'm doing a search use case, I'm typically going to align my shards, both primary and replicas, on counts that are divisible by those data nodes. So 6 is divided by 3 easily. In this case, I have 3 data nodes. If I have 6 shards, I'm going to distribute 2 shards across each data node. They should typically be the same size, and I'm not going to have any data skew. Everything's be evenly distributed, and the data nodes should perform similarly in my search use cases. And this allows me to distribute the load evenly across those nodes so I can engage all the CPU and the JVM to get the full performance I need. You typically use replicas for durability, but you can also use them for throughput, so you can actually get more performance. Add a few more replicas, and you can push through a lot more throughput up to a certain point. And it's really dependent on the hardware that you're leveraging for your deployment. Finally, if you use a 3AZ pattern and with 2 replicas on the data, it extends that durability and also gives you that increased throughput. The next one is when we look at small data. A while back, I was working with a customer that had a very, very large data node footprint and a very, very small data set. When the data set was deployed, it was the whole aggregate index was 5 meg-ish, and it was deployed across a multitude of instances. In reality, Elasticsearch does really well with 1 shard for serving data. And what the customer had done was they had split that 1 corpus of data into very, very small shards across a large number of data nodes, and you get what's called scatter gather. Well, a rule of thumb that I use is if all your data is going to fit into 1 shard, up to 50 gig, and there's some caveats with search use cases. I usually target 25 or 30 gig. But if you look at how this works, you can apply what's called data locality for small data. And if 1 shard can serve that request, multiple 1 shards across data nodes can serve multiple requests and have heavier throughput, and you get what's called data locality. And what this means is that all the data lives in 1 shard on 1 data node. You can leverage things such as file system cache to improve the query time by indexing norms or other parts of the documents that can leverage the remaining remaining cache that's on a data node to help you serve a lot quicker. One of the anti-patterns I see is breaking small index into multiple small shards. If you have an index, it's a few meg, don't split it, keep it in 1 shard. If you have an index that's even a few gig, even up to 50 gig, you don't necessarily have to split it into multiple shards, keep it in 1. And if you want to have that throughput, then have replica shards that with the combination of the primary and the replicas equals the data node count. And if you need more throughput, just go ahead and add more replica shards to your data nodes. Also, another key trick here is to use the local attribute to make sure that that query stays on that data node and you don't get any scatter gather, because you know that all your data lives in 1 shard. There's no need to talk to any other data nodes. So looking at this, if you want to get more scale, you can add more replica shards. And those replica shards will allow you to scale up to a certain point. Keep an eye on JVM and CPU. These usually will tell you that you're overdriving your data nodes and you might need to scale wider. In a search use case, if you scale wider, just make sure that your shard counts are evenly divisible, and that if you are using the data local option, that those counts will line up. In this case, I have 1 primary shard, 5 replicas. That's a total of 6 shards across 3 data nodes, 2 shards per node. And that will allow in this specific use case for me to get optimal performance and distribution of data. If I need more, I can add more data nodes if that CPU and JVM are constrained, and I need to just make sure that I update and keep my specific nodes in that count that I talked about, an even distribution of data, even counts or divisible counts of the primary replica shard count itself. So let's look at the anatomy of a simple search solution, and I'll drop into the demo here. First of all, when you set up a search solution, you typically want to have the Amazon Elasticsearch service in a private environment. And the Amazon Elasticsearch service offers what's called VPC. To get the scale that you need, you can have multiple subnets that can help you with durability and availability. And as you scale your solution, it gives you multiple network interfaces in which you can interact with the service. Now, when you stand up the Amazon Elasticsearch service, you will choose multiple subnets inside that VPC for your private traffic, and these will present ENIs to help with your scaling activities. Next, what you want to do with your search application is have some API layer. I typically like to decouple my search engine from the APIs so that if I have to do maintenance or I have to do other activities where I use a facade, I don't have to have a direct query go into the Amazon Elasticsearch service, and I can build other protection mechanisms such as caching layers and other things that then could stop users from doing repetitive queries that might DDoS my service. Finally, you want to have an application layer that you're going to serve your web application from. This could be statically hosted, or you can use EC2 instances or containers behind a load balancer from which your users can then access that service. And really that's it in a nutshell for a search application outside of the ingest processes. But this is the core fundamental thing that you'll have. You might use a web-based React framework, and in this example that I can provide, actually does that. So let's go ahead and let's do a demo of the simple search solution. So what I've prepared for you today is a demo that uses the framework that I discussed, which we have an application layer that's hosted by EC2 instances behind a load balancer. It uses API gateway and Lambda to provide a facade or an abstraction layer between the application, the Amazon Elasticsearch service, and it leverages a movies database on the Amazon Elasticsearch service. And so what I've done is I've stood this up with CloudFormation. I've built a complete end-to-end solution that took me roughly 25 minutes to deploy. So if we navigate to the CloudFormation service itself, and we go to the console, I will see a series of stacks that I created. And my core stack that is out there has orchestrated the networking layers, service link roles, access for administration through Cognito, the Amazon Elasticsearch domain, API gateway, a proxy server so I can navigate to Kibana console from the public space, and the application layer, which is a React framework that will be presented in your web service. And the results of this provide me with some outputs that present my solution. In those outputs, I have details such as the Elasticsearch domain name, my one-time password to get in Kibana, which we'll use to show the indexing capabilities, and also my endpoint for my proxy and my solution. Now, if I click on the solution right now, there is no data, so I need to go ahead and prepare this data. So what I'm going to do, first of all, is I'm going to make sure that I can get into Kibana with my one-time password, and I'm going to navigate to the proxy service itself. So I'm going to copy the link address, navigate to the console. I'm going to drill in. Since I am doing self-signed certs, it will give you your connection is not private. This is okay because self-signed certs, I don't expect it to have a certificate of authority to find. So I'm going to click on the advanced button. Browsers have different implementations. I am using the Chrome browser here, but you can use any other browser. But you're going to have to, through your access policies, allow navigation to go to what they would call an unsafe environment. In this case, it's safe. So I navigate. I get presented with a login screen. I'm going to go ahead and enter in the user that I found in the CloudFormation stack. I am also going to enter in the password. Now you want to be very, very conscious when you do cut and paste that there are no spaces in here. So what I usually do is I have a notepad or something that I can ensure that there's nothing control character-ish that's going to cause my sign-in to fail. And I provide my one-time password, and it will force me to sign on and create a new one. So I will go ahead and create the new password. I will validate. And I should be into the console for Kibana. Given I'm using a proxy server, it's going to take just a little bit more time to resolve things. But in the end, I have a solution, and I'll go ahead and navigate to the things that are relevant. So first of all, I'm going to go ahead and navigate to the developer tools so that I can look at, what indexes I have available on this Amazon Elasticsearch service domain. Right now, I shouldn't find anything, but let's just go ahead and navigate to developer tools. So my developer tools are just about loaded up, and here shortly in a second, I will be able to see an interactive console that will allow me to navigate all the index details on my cluster. So in the console, what I'll get presented with is a command line set here. And first of all, I'm going to verify I have no data on this cluster. So I'm going to do a get underscore cat indices. This just tells me, do I have anything out there other than my open distro security plugins and the other things that define properties for myself and the cluster itself. So I see that there are no indexes out there that are relevant to movies. So now that I have access to the server, I'm going to navigate over to System Manager. So I'll pick on my service, I'm going to open and link in a new tab. I'm going to navigate to Systems Manager. And System Manager is going to give me a secure backend access to my proxy server that gives me the command set that I'll use to seed the domain. So when you're looking to build a scalable solution, you're going to need some way to automate or script out some of the work that you want to do. I'm just abstracting this with the concept of using a proxy server that's used with the Systems Manager console. System Manager means that I don't have to use SSH or potentially compromise my solution with an SSH public-facing activity. But I'll go into my managed instances, and I will navigate to the proxy server itself. I can see that I have a React server that's out there. I'm not interested in that. I want to go ahead and start a session on the Kibana proxy. Now, some of the things that I have in here are some tools that help me seed the domain. And what I'm going to do is make sure that I am using the SSM user. So I will do a CD, and I'll do a PWD, get me into the working directory. And this will allow me to start executing my commands. One of the things I need to do to make sure that this proxy server can actually talk to the Amazon Elasticsearch domain, given that we have the fine-grained access control plugin, is I need to go ahead and allow that to happen. We have a security plugin, and that security plugin is going to load. In the background, I'm going to grab some more details that were exposed. And this right now is I need a role ARN for the fine-grained access control to filter on. And this is going to allow me to use my instance use the instance role to then allow or deny access. So let me copy this. So now that the role mappings have been identified, I click into that, and I will see that I have an all access role and a security manager role. I'm only interested in editing the all access role so my proxy server can talk to the Amazon Elasticsearch service using the fine-grained access control plugin. So we'll add the first role, which is going to be my Kibana proxy. Also, since I'm using Lambda, I want to make sure that I grab the Lambda API role, and I present that also to the fine-grained access control plugin, so that will allow communication from that service too. So I always need to make sure that there are no spaces in here. And again, I can use a notepad to do this. Once I've updated these roles, I go ahead and submit that. And now it means that I have 3 roles: my admin user, or the owner of the domain, my proxy, so I can execute commands against the service programmatically, and my API gateway lambda coupling that gives me the ability to execute commands from a search perspective. So let's go ahead and seed the domain. So I will go over to my notepad, and first of all, I have a proxy that validates I can actually talk to the service itself. And what this will do is it will allow me to download the tools needed to talk to the service. So again, what it's going to do is going to validate that I have connectivity, and I should expect to see a result that says, for search in the tagline. And I have connectivity, so let me go ahead and execute the next script. And the next script is going to be my commands to populate a index template and to populate the data. So I'll go ahead and execute that script. And it does all the commands that will present the index mapping, and it will add the data to the service. There's roughly 5,000 documents that are out there. And now that my domain is seeded, let's go back and we'll do a real quick query in Developer Tools and take a look at what that data looks like. So now if I perform cat indices, I will see that I actually have a movies database. And it has basically primary shard, 2 replicas. And when we talk about our scaling activities, I'll discuss what this means. But it tells me that there's 5,000 documents in there, and the total corpus of data is 4 meg. So I really only need 1 primary shard to serve this search workload right now. The other thing we can look at is let's look at get underscore cat templates. And let's go ahead and execute that. Now we'll see that I have a movies template in here, and the movies template is going to define what my mappings are. And so if I do get slash movies and underscore mapping, I will see that the template provides me with mappings for that data. And I have a broad range of data types in here that allow me to interrogate the data. The final thing I want to do is verify that I actually have some data in there. So I'll do actually up top here, I will get movies and do a quick search, and I should see some data gets returned. I will see that there are a bunch of movie entries in here, talk about things about the movies. So let's go ahead and let's look at the application. One of the things in the CloudFormation stack is an application URL. I'll go ahead and hit that endpoint, and I will go ahead and search. And let's go look for Iron Man. So when I start typing, I will see something called Iron Man. So what this is basically a search on the backside that's going to query my data set, and it's going to find details about that movie. Now, if I look on the left-hand side, we'll see that I have other levers. So let's say that I don't want to look at Iron Man. Let's say that I want to find movies that are, maybe between a 3 and a 7. So what I can do is I can adjust the slider to add or remove movies that I think would be relevant to what I want to see. Maybe I just want to see all movies that are a 9 and a 10. And, these are, through the IMDb movie ratings. It could be Shawshank Redemption, The Dark Knight, Pulp Fiction, and The Godfather. But let's say I really have a place in my heart for Al Pacino. I want to see his movie. So we got The Godfather, classic movie, and I can further narrow down. Now I'm going to guess that, crime and drama are part of this, so I'm not going to further filter on The Godfather. But, you can also say, I also want to have movies with Al Pacino and Robert De Niro. And that's going to tell me that only The Godfather Part 2 has that. So if we look on the side, these things that we have here are called facets. And the facets could be genres, actors or directors, or other key pieces of data. And we can see as I slide this bar over and I start addressing and looking at these things, that the counts will actually be shown for the number of movies that match these criteria. So when you start looking at a secure and scalable search solution, you can leverage the framework that we have with the Amazon Elasticsearch service. The final thing I want to touch on is the scalability of the service. So it's not enough that I can go ahead and present these movies to my users or my customers. Let's say that I'm starting a movie business. and I want to have people scour my streaming movies database. But let's say I need on the order of tens of thousands, if not hundreds of thousands of users per hour. How am I going to address that? How am I going to get that scale? Well, one of the great things about the Amazon Elasticsearch service is that we can go in and we can modify the dimensions of the cluster itself. So the way that we do that is we go to the Amazon Elasticsearch service. As I mentioned earlier in discussion, that you can scale your cluster with a few clicks of the console. Now, most of us are actually going to go and we're going to scale our clusters using programmatic APIs or CLIs. We're using Terraform or CloudFormation. But in the end, what we're going to want to do is make sure that we can scale our clusters to meet the workload. In this case, we're going to use an example. And what I'm going to want to do is I've done my calculations and I decide that to serve my expected customers, I'm going to need to have at least 6 data nodes. And this is an example, this is not reality. And what I want to do is add more data nodes so I can serve my requests. The other thing too is that my example domain, I've not put master nodes for my durability and availability. And when you're talking about scale, you want to have master nodes that control the state of the cluster while the data nodes focus on serving the actual content itself. So what I can do is I can go into actions. I can go to edit domain and I can update my approach. Now, I right now have 1 availability zone, but let me choose 3 AZs. And I'm going to have 3 data nodes. I'll go ahead and use maybe a C5 large set of instances, which are pretty typical for use cases. I'll probably use an extra large with some more CPUs and JVM. I'm going to use the storage type EBS, and since I only have 4 gig of data, my sizes don't need to be large. So I'll just take the default for this. So as the shards distribute, I'm going to have 5 gig of data per node. So I have, in this case, I mentioned I would want to have actually 6 data nodes. So we'll go ahead and modify that. And I'll go ahead and enable dedicated master nodes. Our rule of thumb for master nodes is anything under 10 nodes or 2,500 shards. Let's go ahead and use a C5 large. So I will go ahead and pull a C5 large offering, 3 default, and all the other bells and whistles are in here. What I need to do is I need to select the subnets. In here I have private subnets, so I'll do private app 1, I'll do private app subnet 2, and private app subnet 3. So I now have multiple availability zones to address scale and durability. Everything else is already enabled. I need to do no more changes, and I'll go ahead and submit that. Now at this point in time, the cluster is going to scale for you. As I mentioned in our conversation, while the cluster is scaling, guess what I can do? I can still serve my workload. So we talked about 0 downtime. I'll go ahead and serve my workload. So let's go ahead and run another search. So in this case, I might want to search for, let's not use Iron Man. Let's use, something like Arnold Schwarzenegger. So let me just go ahead and search for Schwarzenegger. ISC, I need to learn how to spell properly. Let me go ahead and take off my facets and my filters and clear all my filters. And we'll see that, guess what? We have things such as Jingle All the Way, which, probably not the movie I want to see, but maybe Escape Plan. Let's just go ahead and change this to Terminator. And Terminator. And now I'm pulling up, my favorite movies, a lot of, cyborg activity and, crazy science fiction stuff. So in the end now, I have a cluster that's running in the background. I'm actually still serving content. So the way that you can manage your scale concerns and have a scalable search offering is leverage a combination of the management APIs for the Amazon Elasticsearch service to give you that ability to scale as your workload needs are required. So as demand increases, I can scale up. As demand decreases, I can scale back down. And all I need to do is make sure that I have enough copies of my data. The final thing I need to do to address the scale here is, remember, I established a particular shard count. And if I look at my CAD indices, we'll see that when I go in here, I actually only have 1 primary shard and 2 replicas. Well, guess what? that means that 3 of those data nodes that just spun up are not going to do any work. So what I need to do is I need to allow more replicas of my data. Since I have 6 data nodes, I want to have 1 primary and 5 replicas. And that way I can get some data locality and distribute that data across those shards and across those data nodes. So the final thing I'm going to do is I'm actually going to change my settings. And I'm going to change the number of replicas to 5. And so the way that we do this is we again use the CAD API. Since I have admin access, I will change the settings on this. And let me just remove some of the white space so that I don't get yelled at by the editor. And I'm going to change my number of replicas to 5. And I'm going to execute the command. And what will happen is it'll say acknowledged equals true. If I go back and look at CAD indices, I will see now that my number of replicas equals 5. What's happening right now is the data is being then evenly distributed across those data nodes. And as I go ahead and review the domain, I will be able to see once the cluster has finally upgraded itself and put things into play, and those data nodes that have additively been put on the domain have been fully stood up, then I would expect to see even distribution of that data across the cluster itself. So this concludes the demo, and we'll just go ahead and open this up for questions.